Now we are moving on to section 13.3, circle theorems. Now class, for circle theorems, all the circle properties that we have learned in Emaths are applicable here. In fact, you must know all the circle properties of your Emaths in order to do all this section here. Okay, now I will straight away go into example 8. Okay, now example 8 is trying to tell us that we are to prove OBP is an equilateral triangle. Now we know that in order to prove that it is an equilateral triangle, we must either prove 3 angles the same or 3 sides the same. Okay, now let's take a look at this. They give you that this is 30 degrees. Now because this is the radius, this is also 30. Now this is a diameter, therefore this is 90 degrees. So this is 60. Because this is radius, this is also 60. So if this is 60, this is 60, this will follow to be 60 because it's angle sum of triangle, and therefore OBP is an equilateral triangle. Now of course we cannot just say in this way. Okay, we have to write out the proof formally. Alright, so this is how we write out the proof formally. Okay, we say that OPA is 30, base angles isosceles. This is 90 because it's right angle in semicircle. Therefore, when we deduct, we get this as 60. Now, angle OBP is also 60 because it's base angles isosceles triangle. Then we use angle sum of triangle to find that this is also 60. And therefore, we conclude that it is an equilateral triangle. Okay, so this is your example 8. Now, your example 9. Okay, they want us to prove that angle ACD, this angle is equals to BDC, this angle. Okay, now we use, first of all, alternate angles, then we use angles in the same segment. BDC and BDC and CAB, they are angles in the same segment. Okay, so they are equal. So we prove that angle ACD is equals to angle BDC. Okay, as required by the first part. Alright, as required by the first part. Next, we are supposed to prove that AC is equals to BD. Alright, now, because these two angles are equal, this is an isosceles triangle, we will have EC equals to ED. Alright, this is from the isosceles triangle property. Now, then we have alternate angles in the same segment. So, triangle AEB is isosceles with EB equals to EA. We know that EC is this. We plug in the equivalent. Okay, is BD. So we have proven that AC is equals to BD. Alright, AC is equals to BD. Now, last of all, they want us to prove that triangles ACD and BDC are congruent. So, we use the result from part 1, part 2 and a common side. Okay, you can prove that it's the congruent triangles by using the SAS property. Okay, by using the SAS property. Alright, now I'm moving on to example 10. Now for example 10, I'm doing it slightly different from the textbook because I find that the textbook may not be that comprehensive because they use a lot of words. First of all, they want us to prove that triangle AXP is similar to triangle YBP. Now I let this angle be theta, angle PBY will be 180 minus theta because this is adjacent angles on straight line. Now this is also 180 minus theta because this is a cyclic quad. These two add up to 180. Okay, but this is 180 minus theta, this is 180 minus theta, therefore these two angles are equal. Okay, now likewise, if I let this be alpha, this is 180 minus alpha, this will also be 180 minus alpha because they are opposite angles of cyclic quad. Okay, so we have triangle AXP is similar to triangle YBP because of AA similarity. We have already proven that two angles are the same. Okay, now next part, prove that we are supposed to prove this. We use the similar triangles property. write it down, okay, then we cross multiply, we will get the necessary result. Okay, we will get the necessary result. Now, if you are not comfortable with using angle ABC or XYZ, that kind of thing, you can always put it as theta or alpha, then you work from there. It's also perfectly fine, but make sure you indicate it. Don't just assume people know. That's very bad. Okay, so that is your example 10. Next, example 11. Okay, it's quite a long one. Alright, now I'm going to explain this. First part. Okay, example 11. First part. Okay, prove that M is the midpoint of PK. M is the midpoint of PK. Now, take note, PM is MC. PM is MC. Because this is the external point, these two tangents will be the same. Tangent from external point. MK is MC. And tangent from external point also. Here, here. Okay, so therefore, PM must be equal to MK. Therefore, M is the midpoint of PK. Alright. Now, next, we are supposed to prove that AM is perpendicular to MB. Now, this is slightly more difficult. Now, we are supposed to draw, okay, two lines in order to get this done properly. Now, I'm going to add in two lines. Okay, here and here. These two red lines I have already added in. Okay, now you will realize that angle AMC, AMP are the same, angle BMC, BMK are the same, tangent properties. Okay, so I add up all these because they form a straight line. It will be 180 degrees. Now because they're the same, I can replace. I divide throughout by 2, I get 90. Okay, AMC plus BMC. AMC plus BMC is actually AMB. So it's 90 degrees, so I prove that it's perpendicular. Okay, now to prove the similarity, I again use AA similarity. Okay, I prove that this is 90 degrees, this is a common angle, then this will be similar due to AA similarity property. Alright, okay, next, I'm moving on to the alternate segment theorem. This is another property that we have to know, and this is called alternate segment theorem, or you can also call it the tangent chord theorem, but I will always refer it to alternate segment theorem. Now, what does it say? The angle between a tangent and a chord drawn at the point of contact is equal to the angle subtended by the chord in the alternate segment. So if AT is a tangent to the circle at A, then angle BAT is equal to angle APB. Now the proof is found on page 181 of your textbook. Now I'm going to explain what's this alternate segment theorem. Can you see this is a tangent, this is a chord. Okay, alright. This is a tangent, this is a chord. This will be the angle formed by the tangent and the chord. Now, can you see that from this chord, I project this way? This is another angle here. What it means is these two angles are the same. It's called the alternate segment theorem. Now, I'm going to give you another example. All of you look here. Let's say I have a tangent here. I have a chord. Okay, this is the angle. Alright, now if I project this, this will be the angle in the alternate segment, and these two angles will be the same. Now it need not always be horizontal. You can flip it anywhere, rotate it, okay, so that you can see the alternate segment theorem. Okay, now let me draw you another orientation. Supposing this is a tangent, this is a chord. Okay, this is the angle formed by the tangent and the chord. Now I project this. This will be the angle that is equal. Okay, so this will be the alternate segment theorem. Alright, okay, now for example 12, okay, it's quite tedious. and I have not used the same way as the textbook, so you may want to look at my solution, okay, to see if you understand it. Alright, they say prove that angle PQR is 2 times angle ABC. Alternate segment theorem, exterior angle of triangle. Now this one I'm going to explain. What about exterior angle of triangle? If I have two angles here, this one will be the sum of these two angles. Supposing this is A, this is B. This angle is A plus B. This is called exterior angle of triangle. That's how I get this particular answer. Go through it and see if you know what I'm talking about. Okay? Now next, deduce a similar result for angle PRQ. I do it the same way. I found out that angle PRQ is actually 2 times the angle of ACB. Alright? Now the last part is the difficult part. Prove that 2 times angle this is equals to this. Now I have labeled the angles in terms of theta and alpha. You can see I labeled this angle as theta, this angle as alpha. Okay? So in triangle ABC, angle BAC is 180 minus theta plus alpha, angle sum of triangle. Okay, I've shown you this, and I replace by the property in 1 and 2. I get this. Now this is gotten by I multiply 2 throughout this, 2 to this side, 2 to this side. So I multiply 2, I expand. Now I'm going to rewrite this. 360 is 180 plus 180 minus this. Now can you see that this is actually QPR? So I replace. Therefore I get the answer. Okay? The textbook has presented it otherwise, and it's quite complicated. Alright? Now please look through this solution again so that you can understand what I'm talking about. Okay class? Please pay attention because this is very important in improving. Okay? So that will be your example 12. Okay? Now that will conclude the whole of the circle theorems. Now in this chapter there are 3 sections: triangle theorems, quadrilateral theorems, and circle theorems. In the circle theorem, there's only one extra property that we use, and that is the alternate segment theorem. Okay, in addition to all the Emacs questions or Emacs properties that we have learned in our Sec 3 syllabus. Okay, now for this exercise 19.3, you are going to do these questions for me. Question 1, question 4, question 5, question 8. Yes, 1, 4, 5, 8. 4 questions here for you to do on the foolscap paper, okay, before you refer to the answer video later.